our 13th lecture for the Organic Chemistry Summer Program. Today, we're going to be talking about the big four reactions that we've covered over the past couple of days, SN1, SN2, E1, and E2, as well as a new concept known as Bredt's rule. So something to keep in mind as we try to figure out which reactions will occur in which circumstances. Remember that reactions often do come in pairs, so sometimes there's more than one correct answer. For example, SN1 reactions frequently accompany E1 reactions, while SN2 reactions frequently accompany E2 reactions. And we'll talk a little bit more about when and why that may be the case. Alrighty, so this slide has a good example of a type of problem that you could expect to see on an OCSP or Chem 37B test or homework assignment. We have starting material, we have an arrow with two different molecules, one's above it and one's below it, and frequently the instructions will say predict the product. So in order to do that, you're going to have to figure out what type of reaction is occurring. You know, is this going to be some type of elimination product? Will there be a double bond? Will we have substitution going on? Those type of things. So for the first part of the lecture, we're going to focus on the factors that you can use in this scenario to help you determine what type of reaction that you're going to have, and therefore what type of product. So the first factor, which you might have noticed, is of course we have our lovely substrate. Does anybody know what type of substrate that we're looking at right here? I'm just going to highlight it in brown. So this is actually a secondary substrate because our carbon right here is attached to two other carbon groups. And then attached to our substrate is, of course, our leaving group, this OTS, right up here. This is the leaving group, which, as the name implies, and you've seen before, it leaves in these different reactions. And now we can look over at our arrow. Right above the arrow, we have our nucleophile. This might be a little bit confusing to some because we do have our spectator ion. Anytime you see sodium, know that sodium has like a positive charge, it's a cation, and the SH that has a minus charge. So these two ions are associated together to balance off the charge. And it's specifically the SH minus that's the nucleophile. So I'll go ahead and shade that. And then here we also have a solvent. I know we talked about solvents on Friday. Does anyone happen to remember what type of solvent DMSO is? So DMSO is actually a polar aprotic solvent. So I'm going to go ahead and shade that in as well. And keep in mind that not all reactions will have all of these same clues. For example, some reactions might feature a base. Some reactions, like our solvolysis reaction, will only have our solvent. So every sort of problem is going to be a little bit different, but we're going to talk about how we can use each of these factors to try and determine what type of product we're going to have. Alrighty. So the first salt factor that we can use to try and figure out what type of reaction we're going to have is we can look at our substrate. If you see a primary substrate, then you can pretty much rule out SN1 and E1 reactions, and you're going to have an SN2 and or an E2 reaction. So this is an example of a primary substrate. As you might remember, primary substrates are not great for SN1 and E1 reactions just because those reactions feature a carbocation intermediate. And primary carbons are not really very stable to have that carbocation. So one-step reactions are going to be a better idea than having an intermediate that's going to be super unstable. Now, on the other end of the spectrum, let's say you have a tertiary substrate or something that looks like this. In that case, you're going to have a lot of different carbon groups attached, as we see here. So it's going to be very difficult to perform the backside attack that's featured in the SN2 reaction. So that's why we see all of these other reactions, literally the SN1, the E1, and the E2 on tertiary substrates, but we can rule out SN2 if we see a tertiary substrate. This is super great for having a carbocation because tertiary carbocations are the most stable. However, not so great for an SN2 reaction due to steric hindrance. Lastly, if we see a secondary substrate or something that looks like our example from earlier, we aren't going to be able to rule out any of the four reactions. And this is because a secondary carbocation is still stable enough to form, actually. So you can have your SN1 and your E1 reactions. However, it's not so sterically hindered that you couldn't have a backside attack form. So you'll still see SN2 reactions as well. Are there any questions about using substrates?
Just above or below the primary substrate where you wrote not stable for carbocation, what's the word next to carbocation?
Intermediate, sorry.
Okay, thank you.
I'll rewrite it. Are there any other questions? Okay, I'm going to move on and talk about how we can use the substrate, if there is one, to determine what type of reaction we're going to have. As you might remember from Friday, polar protic solvents favor the SN1 and E1 reactions. And this is because they have both cation and anion solvation. So they'll stabilize that carbocation intermediate. And some examples of polar protic solvents that you should probably get familiar with include water and alcohols such as methanol. On the other hand, polar aprotic solvents like the DMSO that we saw earlier, those favor SN2 reactions. And this is because they only have cation solvation and not anion solvation. And this allows a strong negatively charged nucleophile to move quickly and do the backside attack. And then lastly, note that E2 reactions can occur in either polar aprotic or polar aprotic or polar protic solvents. So if you see one of these solvents, you can use it to rule out either SN1 or E1 or SN2 reactions, but this factor is not quite as helpful for determining whether an E2 reaction will occur. Are there any questions about solvents? Alrighty. Our next factor to look at when we're trying to figure out what type of reaction are we going to have, what's our product going to be, is to think about the attacking molecule. And I use the term attacking molecule here because we could be seeing either a nucleophile, a molecule that's a base, or a molecule that can function as both a nucleophile and a base. So let's look at some molecules that only act as nucleophiles. And this is just a handy list of examples to consider. Typically, molecules that only act as nucleophiles are going to be featured in SN1 and SN2 reactions. And this is because substitution reactions need a molecule that acts as a nucleophile, while E1 and E2 molecules need a molecule that can act as a base. So some molecules that act only as nucleophiles include SH-, H2S, and any of the halides. You might recognize that these guys are the conjugate bases of all the strong acids. Strong acids make very weak bases. Therefore, these guys are too weak to function as a base for an elimination reaction. Next, we have molecules that can be both strong nucleophiles and strong bases. And because of the word strong, that's key here, these molecules are going to be featured usually in SN2 and E2 reactions because you need a strong nucleophile and or base to do a concerted reaction. So some examples of molecules that are both strong nucleophiles and strong bases, we've got the hydroxide ion, we've got OCH3, and there are a lot of other examples which you've probably seen already. Lastly, we have molecules that only act as strong bases. So these molecules include NaH. You might not have known that H can actually function as a pretty strong base. And again, the sodium is just a spectator ion to balance out that negative charge. And then we have tert butoxide, whose formula is listed here and its structure is listed here. We've talked about this a little bit before, but because of its steric hindrance, it's not really able to act as a nucleophile. And it's also what we refer to as a big, bulky base. So molecules that are only strong bases are frequently featured in E2 reactions. So anytime I see tert butoxide, I automatically think, oh, there's an E2 reaction going on. Alrighty. And then we have molecules that are weak nucleophiles and bases. You probably recognize by now water and methanol, which are featured in Solvent reactions a lot because they are polar protic solvents. Solvent reactions generally do SN1 and E1 reactions just because the molecules are specifically weak nucleophiles and bases. Are there any questions? Alrighty, let's keep moving then. We also should consider the effects of these different solvents on nucleophiles. This sort of topic is frequently tested in both OCSP and Chem 3570, where you'll be given a set of nucleophiles and the professor will say, rate these solvents from strongest to weakest, where the strongest nucleophiles are able to react the fastest, and the weakest nucleophiles react the slowest. Oftentimes, the nucleophiles that are used in these types of problems are halogens because it's very easy to compare them size-wise since they're just one atom and they're all on the periodic table. So if you had nucleophiles that were the same size, the solvent would have equal effects on them. However, it would be kind of boring to give somebody a problem where all the nucleophiles were the same size. So let's consider some examples where you have nucleophiles that are different sizes, specifically the halogens. So if you have a polar aprotic solvent, a smaller nucleophile is going to be a better nucleophile or react faster. If you remember, polar aprotic solvents do not have any anion solvation and they don't have hydrogen bonding going on. And this makes it easier for a smaller nucleophile to move faster. In polar protic solvents, however, larger nucleophiles are better. And this is because there's both anion and cation solvation, as well as hydrogen bonding. So you're going to be able to have a lot more intermolecular interactions. And the larger your atom or molecule is, the easier it can kind of push through those different intermolecular interactions. So as an example, let's draw iodine. It's the biggest of the halogens. And we'll draw some water molecules that are trying to form their interactions, but the iodine is just so big that it kind of pushes through everything and is still able to go and perform its reaction. Any questions about solvent effects on nucleophiles? We will be doing a practice problem in a moment where we can think about what we have just learned here. Alrighty, let's take a look at our practice problem. Again, this is the type of problem that I was referencing where we have a bunch of nucleophiles. They are all the conjugate bases for the strong acids. And here they specify that we have a solvent. Does anyone remember what type of solvent DMSO is? I know I've said it multiple times during this lecture.
Polar aprotic.
Thank you, Noah. Yep, DMSO is polar aprotic. So we're going to go ahead and rank these nucleophiles, with 1 being the strongest or the fastest nucleophile, while 4 is the slowest or the weakest nucleophile. So in polar aprotic solvents, which type of nucleophile is the fastest or the best? Is it a smaller nucleophile or a bigger nucleophile? Thank you. Somebody said that it is smaller nucleophiles. So if we were to look at the periodic table, there is a column close to the right-hand side. We see fluorine is in the first row, and then if we go down a row, we see that there's chlorine right there. Then we have bromine right in the next row, and lastly, we have iodine because I mentioned that was the biggest. And if we go by that order, fluorine is going to be the fastest to react in DMSO, and chlorine next, bromine third, lastly iodine, just because it's the biggest. Alrighty, so that's what would happen if we were in polar aprotic solvent, like DMSO. Suppose we had a polar protic solvent, however. How would our order of nucleophiles look differently? Well, if we remember from the last slide, In polar protic solvents, larger nucleophiles are better just because they can push through all of the additional intermolecular reactions that occur in polar protic solvents compared to polar aprotic solvents. So that is why our order is actually going to be reversed, with iodine is the fastest and fluorine is the slowest, and the order of chlorine and bromine will be switched as well. Are there any questions about this? Alrighty. One other factor that you might want to consider as we're looking at these types of problems where they're saying predict the product, you know, what type of reaction is going to occur, and also specifically, what is the major reaction that's going to occur? What's the major product? Heat specifically favors E1 reactions. And the sign for temperature is just this little delta. Hydraulic meter like that. Let's look at an example. I'll draw secondary substrate. The bromine is our leaving group. I'll draw our reaction arrow. 3OH. And I will add our temperature sign. So you guys probably remember by now, CH3OH is a polar protic solvent. It is also a weak nucleophile and base. So we're probably not going to have any SN2 or E2 reactions because it's a weak nucleophile and base. This is likely going to be a solvolysis reaction, especially because this molecule is the only type of attacking molecule that we're given. It's a polar protic solvent. So because we have this temperature sign, our major product in this specific reaction is going to be the E1 reaction, or the E1 product. And if you're wondering, how do they know what product is going to be the major product or the minor product? Well, there's this technique known as spectroscopy, where they can actually analyze the product of a reaction and say, oh, this product has a double bond, this product has a single bond, this product has an alcohol group on it, and they'll be able to tell exactly what the percentage of SN1 substitution product, which would have the alcohol on it, and E1 product, which would have a double bond, and the E1 product in this reaction with the heat would have a higher percentage than the substitution product with the alcohol. Are there any questions? Alrighty, if there are no questions, I will go ahead and pass things over to Sam.
Thank you. Let me go ahead and screen share. Give me 1 second. There we go. Let's see if this will work. Perfect. Can everyone see this? Anyone can't see this? Me doodling?
You're good, Sam.
Perfect. Thank you. As always, please let me know if my Wi-Fi is being bad. I can slow down a little. But basically, now that Sydney has gone over all those different factors, we're actually going to use them in a few examples. So we're going back to our original example. Remember, here's our substrate. If you're curious, this leaving group here, let me highlight it. This is known as toslate. Spelled something like this. And this is something, this is a less common leaving group than say you like halides or something, but you will see it once in a while, hence why we're doing this example. So remember, when you look at an example like this, the way you want to approach it is you want to decide on all the factors. What is happening here? This is the substrate. The toslate is the leaving group. Let me write Lg. And what kind of substrate is this? Anyone want to tell me? Is it primary, secondary, tertiary? What do you guys think?
Secondary.
Perfect, thank you. It is going to be secondary. Remember what we want to do is we want to go ahead and look at that carbon that is attached to the leaving group. We're going to see that it has 1, 2 carbon attachments. So that is a secondary substrate. Next up, what we want to do, let me write substrate real quick, is look at our different solvents. So we have NaSH. Remember, like Sydney mentioned, the most important part here for us is going to be this SH minus. This Na will just be Na plus, spectator ion. So SH minus, you may remember from before, is going to be a strong nucleophile, but really not a great base. So I'm going to say not a strong base. And then we also have DMSO. I went over this a couple times. Polar aprotic solvent. So based on what we know, this polar aprotic solvent, the secondary substrate, what do you guys think might be happening here? Feel free to say in the chat or say out loud. Just shoot something out. All right, thank you for everyone DMing me. There's SN2. Remember, when we have an SN2 reaction, we often have an E2 accompanying it. In this case, we are not going to have an E2 because remember, NaSH, let me do it like this. NaSH, this SH minus is not a great base. We want a good base for an E2. Let me go ahead and show you the SN2 product. Gonna look something like this. Remember, this SH will replace our tosylate because that left. And when we do an SN2, we want to remember to have inversion of stereochemistry. Anyone have questions so far? Let me write that a little bit nicer. All right, let us go on to the next one. Next up, we're going to have the substrate, the solvent. Again, let's look at the substrate. Here's a bromine, that will be our leaving group. And if we look at the carbon that is attached to that bromine, we're going to see it's 1, 2, 3. It's going to be a tertiary carbon. So we have a tertiary substrate. We have CH3OH. And can anyone tell me what kind of solvent that is? All right, you may remember from before, it's going to be polar protic. It's not going to be a strong nucleophile or base. So let me write not a strong nucleophile or base. So remember, for tertiary, generally our options for reactions are going to be SN1, SN1, E1, E2. What did we just say about E2? Remember, E2 is going to want a good base. We can get rid of that. So our options are going to be SN1 and E1. Let me show you what those guys look like. Oh, there's a very terrible pentagon. That is slightly better. We'll go with that. Remember, remove the bromine, put OCH3 on instead. Is going to be your SN1 product. And you'll also have the E1. Here's your E1. And so, like Cindy just mentioned, if you were to have heat, let me write that down. So if you had heat, this little triangle, then your E1 is favored. Any questions? Cool. Last example for this section is going to be this guy. Once again, look at your substrate, chlorine. Hopefully you know that's going to be the leaving group. Look at this carbon. Once again, have a secondary substrate, secondary carbon there. And so we also have this NaOH. And so you may remember that NaOH is going to be a strong base and a strong nucleophile. So let me write that down. Strong base and strong nucleophile. And so if that is the case, you may be thinking, okay, let's write this over here. You can probably have an SN2 or an E2. But recall when you learned about E2s, one, they do need a strong base, and we have that here. We are good in that front. But E2s also require taking off the hydrogen anti to the leaving group. So let me write that down. Take off hydrogen anti to Lg, leaving group. So let's look at our chlorine over here. Remember, we want to look at the adjacent carbons. So this carbon down here below chlorine has two methyls. Can't really do much there. No hydrogens to speak of. But this carbon to the left is going to have this methyl group. Let me just write this in for you. And also a hydrogen, but it's on this wedge, right? And so if this hydrogen is on the wedge, that's not going to be anti to our leaving group. They're both on wedges. They're not on opposite sides. And so E2, for this reason, despite having a good base, is not going to happen. So just our SN2, because remember, this hydrogen is actually syn. So syn 2 chlorine. When we get our SN2 reaction, is going to look something like this. Remember inversion of stereochemistry. So this OH that replaces the Cl is going to be on a dash instead of a wedge. All right. Anyone need a little bit more time to write this down? If not, I'm going to go ahead. Now we're going to be talking a little bit about ring compounds. You may have seen this a little bit previously, but let's go ahead and give them some names. So there's going to be three major classes of ring compounds that you're going to cover. First one's going to be called spirocyclic compounds. Those are two rings sharing one atom. Let me show you what that looks like. It's going to be something like this guy on the left. So you're going to see, there's a pentagon and pentagon, two different rings. They're only connected right at that one point, at this one junction. And so you'll see these kind of crazy names. You'll learn how to name them in 3570. We're not so worried here. We're just going to give you a little introduction. Second compound is going to be known as bicyclic. And so this is going to be two rings sharing two or more atoms. And they can be either classified as fused or bridged. So you're going to see these are two bicyclic compounds. This guy on the bottom, bicyclo-430 nonane, that's going to be fused, while his friend is going to be bridged. Fused, you can see, just means you have these two carbons, they're directly attached to each other. Whereas bridged, as hopefully you can tell, kind of forms what looks like a bridge. So last but not least, you're going to get bicyclic compounds. And those are actually going to be two or more rings. You're going to see differing definitions online, but with many common atoms. So bicyclic compounds, a lot of the times they can be classified as polycyclic. You'll see that they tend to have the bicyclo prefix anyway. And so one example of a polycyclic compound that is not bicyclic is going to be this cubane, this crazy looking guy. As you can imagine, there are a lot of attachments between all these rings. Remember, even a square can be a ring. So let me write that down again. Bicyclic. It's going to be these guys. And spirocyclic is this one. Any questions? All right, now that we covered that, let's do it a little bit more. So I'm going to introduce one last definition here. You're going to see this in 3570, but it's the idea of a bridgehead atom. And so a bridgehead atom is defined as an atom that is part of two or more rings, either in a polycyclic or sometimes a bicyclic molecule. We also write bicyclic. And so the way I like to think about this is it's the carbons at the junctions. Because I know this definition can be a little bit confusing. So let's go ahead and see what that looks like on an actual molecule. This guy on the left, remember, this is going to be a fused bicyclic compound. And so the bridgehead atoms are going to be the ones at these junctions connecting the two rings. Let's go ahead and go to the middle. This one's going to be a little bit more confusing. The bridgehead atoms are actually these two, the carbons at 1 and 4, not actually the carbon at 7. Easy way to remember bridgehead is junctions, like I said. So the way I like to think about this is this has 3 attachments, this has 3 attachments, this really only has 2. Then last but not least, cubane. Remember, okay, this one's bicyclic. Put that in there, bridged. His friend on the right is polycyclic. This cubane is going to have a lot of bridgehead atoms. I think every single atom in there is going to be bridgehead. And so for this reason, you're going to see that some polycyclic molecules, the crazy looking ones like this guy, have a lot. Generally in 3570, you're going to stick to bicyclic because the teachers know these guys are a little bit nuts. But yeah, in case you were curious. And one last thing I want to cover for this part is that you might see, for example, this molecule that we touched on earlier. It could be drawn in a lot of different ways. Same thing goes for a lot of your ringed compounds. So that's just something to be aware of. I know, looking at this for the first time, it can be kind of confusing, like what am I looking at? But remember, these 3 guys are actually all going to be the same. You could probably tell that the one on the left and the one on the right is the same. The only difference is they changed the stereo. Well, they didn't change the stereochemistry, but they showed the stereochemistry here, whereas they really didn't here. But this middle one, the way you can imagine it is it's as if you were looking down from the top carbon, this number 7, looking down the molecule, you would probably see something like this. So if we were to actually count on our carbons, let me go ahead and do that. You're going to see it's the same amount, they're in the same placement, you're just looking at it from a different angle. Cool. And then last but not least, we're going to be talking a little bit about Bredt's rule. And so this is used for bridge bicyclic compounds or bridge bicyclic rings. And so what Bredt's rule is going to say is that for any ring system with less than 8 carbons, it's not less than or equal to, it's just less than, you cannot have a double bond on a bridgehead atom. In this case, bridgehead carbon generally. And so why doesn't this work? The real reason is that when you have these adjacent p orbitals, the C to C double bond doesn't overlap super well when you have a double bond on a bridgehead atom. I think an easier way to understand this, and generally this is how the orgo teachers will show you, is that if you were to try to build this model with the double bond on the bridgehead atom, like you cannot build it, like you'll have to twist it in a way that it doesn't allow you to. So the model is just going to break. And so there are a couple exceptions to this rule. They're called anti-Bredt molecules. Don't worry about them. If your teacher wants you to know them, they will let you know. So we will just be going over Bredt's rule molecules. And so let's look at these 3. Let's decide who is following Bredt's rule. Remember, for this compound, 1 and 4 are going to be our bridgehead carbons or our bridgehead atoms. So let me go ahead and label all those. And so remember, Bredt's rule says for a ring system, less than 8 carbons. This is 7 carbons, so of course, less than 8. You don't want to have a double bond on a bridgehead atom. So let's look at problem number 1. Let me go ahead and zoom in a little. Problem number 1. That's not going to have a double bond on a bridgehead atom. It's only between 2 and 3. So this guy's good to go. Let's look to the next one. This has a double bond between 1 and 2 that is still on a bridgehead atom. We don't like that. That does not follow Bredt's rule. Last but not least, number 3. Once again, same problem. Double bond is attached to carbon 1. This does not follow Bredt's rule. Any questions on that? Awesome. Let me move on to the next one. And so again, just to be more Bredt's rule practice, let's go ahead and go through this. So remember, Bredt's rule is going to be for less than 8 carbons. Ring systems less than 8 carbons. You don't want to have a double bond on a bridgehead. So let's look at these. So the one on the left, that's the one we just did. Remember, bridgehead carbons are going to be at 1 and 4. Double bond is not attached to either. This one is good to go. What about the next one? So the middle one. Lots of carbons here. Let's go ahead and count them. I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Easy to miscount on these guys, so just be careful. And so you're going to note that this, of course, has more than 8 carbons. So even though this double bond is attached to carbon 6, which you can imagine is a bridgehead atom, this is still good to go. Last but not least, this crazy looking guy. When we count, remember you only want to count the carbons that are part of the ring system. So none of these methyls are going to count. These oxygens are not going to count. So 1, 2, 3, 4, 5, 6, 7. This is only going to be 7 carbons, less than 8. So because it's less than 8, and we have this double bond attached to carbon number 4, which is a bridgehead atom, this is not going to follow Bredt's rule. Let me go ahead and circle your bridgeheads for you. Cool. Anyone need a little bit more time on this slide? All right, looks like we're good. Last slide, we're almost there, guys. So one more practice. Which of these could have double bonds at your bridgehead atoms? Remember Bredt's rule, let's go back to it. Bredt's rule is really only going to apply to bridged bicyclic compounds. So you're going to see that this compound right over here is actually not bridged, right? It's going to be a fused bicyclic. Let me write that. So Bredt's rule is not going to apply. This guy can have a double bond. Does not matter. You can put it there, you can put it there, wherever you want. This is good to go. Let's look at our actual bridged bicyclic compounds now. If you went ahead and counted all the carbons in this ring structure, you're going to see it's going to be more than 8. Yep, you can go ahead and put a double bond wherever you want on a bridgehead carbon. It's good to go. It's good to go. Let's look at this one. This one hopefully looks familiar to you. We've done it a couple times now. Remember, this is only 7 carbons. So if we were to put this double bond here, that's going to break Bredt's rule. Be sad. Last but not least, this crazy looking guy. Even more carbons, I believe, than this one. Let me see. Any case, more than 8. So we can go ahead and put that double bond on the bridgehead. Ooh, that's a terrible line. Put that double bond on the bridgehead carbon. All right. Any other questions on this or any other portion of the lecture? Because if not, that is all we had for you today. Yeah, exactly. Victoria asked in the chat, so you need more than 8 carbons to place that double bond? Yeah. So for Bredt's rule, remember that's only going to be for bridged bicyclic compounds. So these 3 guys are going to be bridged because they have this extension up top. And so you're going to want more than 8 carbons so that you can put that double bond on a bridgehead atom. Again, that has to do with p orbital overlap. An easier way to just understand that is when you try to build the model, like you physically cannot, like you'll have to twist the bond and then the model will break and then you'll be sad. But yeah, any less than that, and then it's hard to fit the double bond in. I'm gonna go ahead and stop sharing. Let me know if anyone wanted that slide or another one.